So I'd like to welcome everybody here today, and especially Jeff Hawkins, on behalf of the Computer Science and Engineering's Distinguished Lecture Series and the annual Rockwood Memorial Lecture of the Institute for Neural Computation. Jeff Hawkins grew up on Long Island in a family with a long history of inventing, including an air-cushioned boat that served as a concert platform, which was part of his youth. He has been described as the man who single-handedly revived the handheld computer industry. He's the founder of Palm Computing, where he invented the Palm Pilot, and Handspring, where he invented the Trio. Now, this is particularly appropriate for the Rockwood Memorial Lecture Series because of the fact that it's named in honor of Paul Rockwood, who received his Bachelor of Sciences in Computer Science from UCSD in 1980, and additionally obtained a second degree, a BA in psychology, in 1981, and then started a company, Integral Solutions, in 1983. And his goal was to develop a universal language translator. Unfortunately, he died tragically in a mountaineering accident before he could fulfill this promise. And I think this entrepreneurial spirit is something that we'll see today in Jeff's career. Jeff has an abiding interest in the brain. He was a graduate student at UC Berkeley before founding Palm. And now he has founded the Redwood Neurosciences Institute, which is located at UC Berkeley. He is the co-author of On Intelligence in 2004 with Sandy Blakesley, in which he describes his memory prediction framework for the cortex. He was elected to the National Academy of Engineering in 2003 for his contributions to computing. Now, to turn this theory that you're going to be hearing out today into a useful technology, he created a company called Numenta, which is meant to be provide a software platform for applying this new form of cognitive computing to many different applications. Jeff's given many talks in many different audiences. He brings together computer scientists, neuroscientists, and business people. And then many of you in the audience are from these different groups. He's something of a Johnny Appleseed for this new era of what's been called cognitive computing. And in preparing for this visit, he told me that he was particularly interested in talking to the students, who in fact will be the ones who will be creating the next generation of handheld brain pilots. Jeff Hawkins.
Yeah, the red light came on. I didn't, sorry, Mike, I didn't do it long enough. Okay, thank you, Terry. There's a little bit of an echo now. Hope we can fix that. So this talk came about because in November I gave a talk at the annual Society for Neuroscience conference, which was held here in San Diego. And it was a real honor to speak at that conference. If you don't know it, it's quite large. There's over 30,000 people go to it, neuroscientists. And I was asked to give the opening talk, what they call the Dialogues Lecture. And so it was a big room, 5,000 people or so. And as part of that, they had a panel and some other stuff, and a number of noted scientists were there and helping out. And Terry Sajowski graciously volunteered. So we were spending some time together there. And after I gave that talk, he said, maybe you should give that talk at UCSD. And I said, well, I'd love to do that. And so that's how I ended up getting here. I'm going to give basically that same talk, but I'm going to add some material to it. So if you were at the Society for Neuroscience conference and you heard it, I apologize. You're going to hear a lot of it again. But there is new material here as well. I have more time, and we can do Q&A better than we could do there. And so that's how I ended up down here today. I have a title for my talk, which is not on the screen yet. Somehow I missed that. There we go. It's sort of a grandiose title. I hope it's okay. Computing Beyond Turing. Essentially, we've been building computers for the last 60 years pretty much on the same principles outlined by von Neumann and Turing many years ago. I've always felt that brains don't work on those principles, they work on other principles, and that if we want to build machines that are intelligent, that solve certain problems we've been having troubles with, we need to understand how brains work. So I became very much involved in neuroscience, and I consider myself some ways more of a neuroscientist than a computer scientist. So my talk today is about bridging in both worlds here, and I'm not going to go, if you really want to go deep into neuroscience, I'll take questions on it. If you want to go deeper in some of the machine learning stuff, I'll be happy to take questions on that as well. I don't mind take questions during the talk, although there will be time afterwards, and I'll try to keep, if we do get questions during the talk, just raise your hand and I'll try to accommodate it. Okay, I'm going to start in the past, so I'll just turn that off. We're going to go back 70 years to 1937. And that was the year that Alan Turing wrote the British mathematician, wrote probably the most famous or influential paper in computer science. And if you recall, Alan, this is 10 years before anyone built a digital computer. And Turing was interested in solving certain mathematical problems, but basically understanding what algorithms were and what computing could be and computation could be. And as part of that paper, he proposed a thought experiment, a hypothetical machine, which we now call the Turing machine. And the Turing machine consisted of two parts. I don't know if you teach this to undergraduates these days or not, if you all know this, but one part was paper tape. And the paper tape was divided into squares, and each square would hold a symbol, a mark of some sort. The second part was a box, so just a little box here, and it could do three things. The box could read a symbol off the paper tape, it could move to a new location on the paper tape, and it could write a symbol on the paper tape. And it would do so based on what it was currently reading off the tape and its internal logic. These, of course, are directly analogous to modern-day digital computers. The paper tape is a linear memory system. That's a memory that we use on our computers, and the box is a CPU, and the marks in the tape are both the program and the data. And so all computers have been built on these principles. Turing went on subsequently to show that such a machine could be a universal machine. It could emulate any other machine. Those are his words, a universal machine. And of course, that turned out to be very prophetic and true, because we all use computers today. We model all kinds of things with them. So it's important for my talk to understand why it was a universal machine, because we're going to come back to this a little bit later. What makes a digital computer a universal machine? A large part of it has to do with the memory. The memory in a computer, I'll just use my paper tape as analogous for the memory in a computer, is purely symbolic. Any particular mark or location in the memory could represent anything. A symbol could represent someone's hair color, their age, the temperature outside, a piece of financial data, a snippet of music. The computer itself does not care about it. You can put as many of those symbols in the computer as the memory allows. There's no limit other than just the limit of the memory. And you can order them in any way you want. The computer itself does not care how you structure the data, what it is, where you put it, how much of you have. And of course, then the CPU can do any sort of symbolic operations on that, logical operations on those symbols. So that was what made these computers universal. Turing wrote another very influential paper in 1950. He was interested in computing and intelligence. And he wrote a paper called, I think it was Computing Machines and Intelligence. And he said the following. He said, look, a brain must be some type of machine. He didn't believe in magic. He says brains are just some type of machine. He didn't know how they work. He says, but they're some type of machine. Therefore, computers can emulate brains because computers are universal Turing machines. Therefore, we can make computers intelligent. He didn't want to argue about what intelligence was, so he proposed the famous Turing test as a way of getting around that problem, saying, look, if a person can't tell a human versus a computer by asking it questions, then we'll have to say the computer's intelligent. And so this idea struck a lot of people as making a lot of sense. They said, sure, we should be able to do this. And a lot of people got excited about it. It wasn't until 1957 when computers were really usable enough to actually attempt this. And that was the year the first AI conference came about, the time the word artificial intelligence was used. And that was the Dartmouth conference. And so people said, okay, we'll start building intelligent machines. They originally said, we'll do what Turing suggested. They said, let's have it understand language. So we'll feed a short story or a story into the computer, we'll ask it questions. That turned out to be really, really hard. And no one could figure out how to even make any progress on that. Then they said, let's try some simpler things. Let's have a machine that look at pictures and tell it what the picture is. Or let's have a machine that listens to spoken language and tell it what words are spoken. And let's have a computer that can navigate a robot through a crowded room. All these things turned out to be really, really difficult. In fact, almost no progress was made. In fact, all those problems are unsolved problems today. And so what was the problem? Where did we go wrong? Was Turing wrong? Is a brain not a machine, or a universal Turing machine is not universal? It turns out that the people initially said, well, our computers aren't big enough. They're not powerful enough. And undoubtedly that was true. but that wasn't the root cause of the problem. The root cause of the problem was something that was surprising. I don't think anyone anticipated it, but almost everyone who worked in the AI field or machine intelligence field for a number of years came to the same conclusion. The conclusion was that to make a machine intelligent, to solve those problems, it had to have a lot of knowledge about the world. The machine had to know a lot of things about the world. And it's difficult to know how to get machines to know things about the world. I'm going to read a quote from Patricia Churchland, who happens to be here today, sitting down in front here. I didn't know she was going to be here, so this is totally unplanned. But Patricia is a philosopher and machine learning expert. I don't know what to call you, but you're a philosopher. Not a philosopher. She wrote this in 1990, and she's writing about the difficulties of machine intelligence and AI. Just sort of retrospective on what's been hard and what's been going on. And she said, I'll read this and explain it. She said, realistic performance required that the computer program have an extremely large knowledge base. Constructing the relevant knowledge was problem enough, and was compounded by the problem of how to access just the contextually relevant parts. There's 3 problems she identifies there. One is, for a computer to be intelligent, it has to know an awful lot of stuff. Maybe so much we don't know how to get it, we can't fit it in the computer. 2, we don't know how to extract that knowledge. We don't know how to collect it. What is the knowledge you need to know? And 3, we don't know how to put it in the computer in a way that's useful. These are pretty daunting problems. I'm going to illustrate them now with just a couple little examples, and then we'll talk about how we solve this stuff. All right, so I'm going to talk about, first I'm going to give you, I'm going to show you a short story. I'm going to read it to you, and then I'm going to ask you some questions about it. Here's the short story. It's very short. Mary saw the puppy in the window. She wanted it. Well, what did Mary want? You'd probably say, Mary wanted the puppy. And I'd say, well, how did you know Mary wanted the puppy? How do you know she didn't want the window? And you say, well, puppies are more desirable than windows? That may be true. Not always true, but may be true. But does that mean to understand a story as simple as this, you have to have in your head stored knowledge about the relative desirability of all pairings of possible objects? What if I ask you, could Mary pick up the puppy? You would say, no, there's a window in the way. And I said, well, that means you need to know that windows are things you can see through, but they represent obstacles or physical barriers, but not always, but usually. And I said, what can Mary do if she wanted to pick up the puppy? You could say she could open the window. You might say she could break the window. You might say she goes to the door next to the window into the pet shop. The point is, to even understand a simple story like this, to answer questions about a simple story like this, you have to have a huge amount of knowledge in your head. Huge. Imagine if you had to understand one of your papers you write. How much knowledge would you have to have there? It's an incredible, it's very deceptive. And you think it's such a simple thing, but to understand even the basic prose like this requires huge amounts of knowledge of the world, and we don't know how to get that into the computer. Let me give you another example. This one's in computer vision. I have a friend, a computer science professor, who studies computer vision, and a few years ago he came to me and he said, Jeff, let's create a grand prize, in the DARPA grand prize type of thing, a grand prize in computer vision. We'll put up $1 million prize, meaning I would put up the $1 million prize. And he'd say, and we'll propose this computer vision problem that's really hard, unsolved, and it'll inspire people to solve it. I said, what is that problem? This is Dan Hutenlacher at Cornell. And he says, the problem would be a really challenging one. He says, we'll show pictures of cats and dogs, and the computer has to tell you which is the cat and which is the dog. Now, you might be surprised by this. First of all, you might be surprised that that's worth $1 million. But it turns out that's a completely unsolved problem. And here are pictures of cats and dogs. And I assume that every one of you in the room can easily tell me which is the cat and which is the dog in each of these pairings. A 5-year-old could do it. Probably a 3-year-old could do it. Yet no computer can do this. Now I could ask, what kind of knowledge do you have to solve this problem? What kind of information do you have to store to do this? You might say, well, we'll have to come up with some sort of template for what a cat and a dog looks like. Now, it could be the picture, or it could be some sort of parameterized template, and so on. Turns out that doesn't work. The reason it doesn't work, not even close, is that there is no regular transformation or set of transformations you can make to morph any one of these images into any one of the other images. You can't, there is no set of regular transformations you can take from an unknown to a template that will work. It just doesn't work. You might say, well, we can solve that by storing lots of templates. We'll just store everything we've ever seen. And then we'll compare the unknown image to all the things we've ever seen. Well, that doesn't work on 2 counts. One is we don't have enough memory in our heads to store everything we've ever seen. The images coming in on your eyes are constantly changing. They've never been the same twice in your life. And Even then, you're going to get a novel pattern, and that novel pattern, although you perceptually see it as similar to one of these previous ones, it's going to be a different pattern, and you still have to do the transformation, and it doesn't work. It's very, very hard. But in your head, clearly, you have a lot of knowledge about how cats and dogs work. You can solve this problem. It's in there somehow. You've learned it through years of exposure to cats and dogs, watching them eat and sleep and run in different breeds. You can imagine, you know, a chihuahua doing a dance right now. You've got that stuff in your head. So our question we want to know is, how do brains do this? How do they get that information in their head? How is it stored in a useful way? So that's what we're going to do. Now, I don't want to imply that we haven't made any progress in artificial intelligence in the last 50 years. A lot of great work has been done. But the core problems of knowledge representation, how information is stored in the machine in a way that's useful to solve these kind of problems, has not been solved. All right, now we're going to turn to the present. And we've made a lot of progress on this, actually, in the last few years. Various people have been working on this problem for many, many years, but all the best solutions have something in common. They all use hierarchical representations. And I'm going to talk about what that means. I've approached this from a biological point of view. I've studied brains. I said, well, let's study the brains. Let's look at them as the structure of brains and what the structure of brains tells about how information is stored in them. And I'm going to walk you through that process now just a little bit and show you how this works. And so we're going to do that. We're going to start off by talking about brains just for a few minutes here. To a computer scientist, the most interesting part of the brain is the neocortex. The neocortex is the wrinkly thing that covers the rest of the brain. If I take the skull off, that's the little wrinkly thing you see on top. It's about 60% of the volume of a human brain. All mammals have a neocortex, non-mammals don't. The neocortex is the locus of almost all high-level knowledge that you have about the world. Almost all high-level visual knowledge is stored in the neocortex. Language, high-level motor control, somatosensory, auditory, and so on. Almost everything you can tell me verbally that you know about the world is stored in your neocortex. And it stores a lot of things you can't tell me about. It's not to say that other parts of the brain aren't important, but that's the one we're going to focus on at the moment. Now, we want to know, what about the structure of the neocortex? How does it work? What does the structure tell us about how information is stored? If you take the neocortex out of your head, you find it's a flat sheet. It's a wrinkled sheet. And if you ironed it flat, it would look like this dinner napkin. It's about 1,000 square centimeters in area, 2 to 3 millimeters thick, 30 billion neurons. My dinner napkin is talking, yours is listening right now. And we know a lot about the structure of this sheet of cells. It's amazing to think about it. This is everything you know is stored in this sheet of cells. Now, we know a lot about it. We know that the neocortex is divided into functional regions. Those regions do different things. There's ones for vision and hearing and language and so on. We know that those regions are connected together at about a 40% connectivity rate. We know if region A projects information to region B will always project information back to region A. We know that those connections are asymmetrical, that when one connects one way, it looks different than when it connects backwards. And therefore, we can actually say which is always between any two regions that are connected. We can say which is the feed forward direction, which is the feed backward direction. Now, if you spend many years, decades, doing very difficult biological research, you can map out all the regions of a particular mammal. You can map out their connectivities, and you can make a picture of it. And this has been done for a few animals. I'm now going to show you one. This is a very famous drawing to neuroscientists. This is the map of the macaque-monkey neocortex. Now, if you're a neuroscientist, you almost certainly have seen this picture. It shows up all over the place. It's from two gentlemen, Fellman and Vanessen. If you're a computer science, you probably say, what the hell is that? Bunch of spaghetti looking. It's really not that hard a diagram. Let me just walk you through it. Basically, these little boxes here are regions of the monkey's neocortex. These little boxes. So you see all the different regions. The lines between them are basically the feed forward and feedback pathways. So if they're connected together, there's information going up and down. On the right side of this diagram, we have regions of the monkey's neocortex associated with vision. On the left is somatosensory and motor control. You see many more regions associated with vision on the monkey, on this guy. In this case, sensory data comes in at the bottom of the diagram. So the retina projects to the bottom of these regions here, and information moves up the hierarchy. And on the left-hand side, it's skin and body senses. Okay, now already we can say a fair amount of things about this. We can say, well, this is where the information about the world is stored. And you, by the way, humans have a similar arrangement. I'll come back to that in a moment. But we can just assume this is you too. Okay? First of all, we can say that knowledge is distributed hierarchically. It is distributed, and it's distributed hierarchically. Meaning, if I want to ask, where does this brain store information about what a cat looks like or a dog looks like, it is not in any particular region. It's going to be over several regions. Not all of them, only in the visual areas and certain ones, but it's going to be distributed, and it's going to be distributed in this hierarchical format, meaning some are going to be closer to the input, some are going to be further away. We know that the system is self-training, meaning you can't program it. No one comes along and says, well, here's where we're going to store the cat, and here's where we're going to store the dog, or whatever. It's self-training. Information flows. When you're born, this data structure exists, but it doesn't know much. It doesn't know about the world. It doesn't know about rooms and computers and tears and tables. None of that stuff is in there. It doesn't know a particular language. And through exposure to patterns, these little regions on their own learn to store stuff. They learn to store the knowledge of the world. It's self-training. And the last point on here is a bit of an understatement. It says each region is similar. What I mean by that is it's been known for many, many years, actually 100 years, that if you look at the detailed anatomy of each of these little sections of the cortex, each of these little regions, you'll see a very detailed sort of layering and cell types and connectivity scheme and so on. And it turns out that everywhere you look in the neocortex, with a few exceptions, it looks almost identical. That the microarchitecture of each of these regions look remarkably similar, incredibly so, regardless whether it's doing vision or language or hearing and so on. And it was in 1979 that the physiologist Vernon Mountcastle was the first guy to say, you know what, I don't think they only look the same, I think they're doing the exact same thing. And the proposal that he put forward is that each of these regions, regardless of where it is in the hierarchy, is actually doing the same thing. And what makes a visual region vision is what it's connected to. And what makes an auditory region auditory is what it's connected to. They're all doing the same thing. This is a wonderful discovery. It's the kind of thing we love to see in nature, where we come across like, that simplifies a lot of stuff. It's so amazing that there are many people who don't believe it. They just can't believe it. If you spent your life trying to figure out algorithms for vision, it's hard for you to accept that the same algorithm that the brain uses to solve vision is the one it uses to solve auditory input. But it's true. And there's an overwhelming evidence of supporting this. So now we have a hierarchically distributed memory system where each region is doing the same thing. And it's self-learning. Next thing, I'm going to highlight here a few regions. These ones in yellow are what are called the ventral visual pathway. That's what neuroscientists call it. It's also called the what pathway. These regions are associated most with what things look like. So there's a whole bunch of visual regions, but what things look like here. And so those are, you can see those going down at close to the retina here, all the way up into this IT complex at the top. Now we know a fair number of things about these regions and the cells in them. We know that cells at the bottom of this pathway, close to the eye, respond to very small parts of the visual space, meaning here, 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 and they also respond to very small visual stimuli, like little edges and corners and so on. As you move up the hierarchy, the cells respond to larger parts of visual space, largest parts of temporal space, actually, and also more complex objects. And when you get to the top, you find cells that represent complete objects. These cells become active when you see a particular type of object in any part of your visual space. In the live human, a friend of mine, Christoph Koch, and another scientist actually discovered in a live human, they discovered cells that respond to Bill Clinton. Whenever this person saw any picture of Bill Clinton at the top here, basically any picture of Bill Clinton, that cell would become active, even if the person just visualized it. And we find cells like this all the time. There's mirror cells, there's all kinds of cells. It's the higher up you go in the hierarchy, they represent larger and larger sort of causes in the world. I suppose there probably is a Hillary Clinton cell now, too, and a Barack Obama cell. And I don't know if Hillary and Bill are near each other, but it doesn't matter. There's got to be a lot of them. Yes, Terry, I didn't want to imply that there's only one Bill Clinton cell. There's a lot of Bill Clinton cells. And probably it's not just a purely Bill Clinton cell. Maybe it's a lecherous guy Bill Clinton cell. Who knows? We don't really know. But they do get more and more specific. And we'll come back to that later because all this is done in distributed representations. There's no grandmother cell, particular grandmother cell. I didn't want to leave that impression. Okay, here I'm now showing the same visual regions, but I'm showing them their relative area. That wasn't visible. That wasn't clear in the last slide. This shows you how much area they take of the neocortex. I just turned them into a link on the line there. So again, now we see these yellow pathways, or the what pathway, the ventral pathway. And we can see a couple things that are surprising. First of all, the two lowest levels here, V1 and V2, are quite large. In the monkey neocortex, they represent 25% of the area of the neocortex. 25%. That means 25% of all the things the monkey has stored in the neocortex, all of its knowledge about the world, is low-level visual information. I would have never guessed this, but that's a fact. Humans are the same way. You have a huge V1 and a huge V2. We can see that these areas get smaller as you go up the hierarchy. So that's interesting. Now, one thing that's misleading about this is it kind of looks like a flow chart. Like, okay, the image comes in and gets processed by V1 and then gets processed by V2 and so on up there. It doesn't really look like that. Here's a caricature drawing of those same regions that I made up. But this sort of reflects closer to the reality. What you see is it's more like the bottom region here. It's not like one little region. It's like a lot of little ones because it's not one big one. It's a lot of little ones. So each one only looks at a small part of the visual space. Any particular area looks at a small part of the visual space. They converge as you go up, and they converge as you go up, and you converge as you go up. And, of course, it diverges as you go down as well. And so we can just stop here for a moment and look at this. This is the data structure that the neocortex uses to store information about the world. This happens to be the macaque's visual neocortex, the what pathway. But it turns out that all the knowledge is stored in a similar hierarchical form. There are regions that they all have the same converging, diverging, sort of inverted tree shape. There's different levels, different number of levels, and so on, different widths, amount of different areas. But they all have this basic structure, a hierarchical tree-shaped structure like this, where sensory information is coming in up from the bottom. And that doesn't look like the paper tape in a Turing machine. And the question we want to ask is, can you understand how this memory system works? If you figure out how this memory system works, you got it nailed. And how hard can that be? Well, it turns out to be reasonably hard, but not that impossible. And the approach that I've taken is I've basically paired up a lot of neurophysiological and neuroanatomical data, like I was walking through here, with a lot of theoretical constraints. And I'm not going to take you to that exercise, but you can add up a whole bunch of things the thing must do. And then you basically work your way up into a theory about how this works. I'm pretty confident I understand the basics of how these memories work, although many of the details are still mysterious. But I'm going to tell it to you right now. I have one slide just telling you how this all works. Essentially, I've given it a name. I've picked a rather boring name. I call it Hierarchical Temporal Memory. I just want it to be descriptive. So hierarchical is obvious. It's temporal because you're going to see in a second that it's all based on time, how time works. Now, again, all the nodes in this hierarchy, these tree-shaped hierarchies, do the same thing. What do? The two basic things to think about it. The first thing they do is they store spatial patterns that occur over and over again, things that occur at the same time. And then it stores sequences of those. Each node is doing this. You can think of a sequence like a melody, it's like a song. If I see a series of intervals in a row and it repeats, I'm going to memorize it. That's a temporal pattern. A common sequence. Now, what a node does is it passes up a constant pattern for the name of the sequence. It's just sort of saying, here, I recognize this melody, but I'm going to give the name of the melody to my parent. And now the parent is looking at a bunch of child nodes, and it's basically getting inputs, which are essentially, it's looking at spatial patterns, which are a collection of sequences. And so it'll learn sequences of sequences. And then you go up there, sequences of sequences of sequences. And the end result is when you have very fast-changing patterns at the bottom of the hierarchy, they slow down in time as you go up. And so my speech is a very complex, fast-changing pattern on the order of milliseconds. But it turns into slower representations that are changing at the higher level of the hierarchy. Each node is also, since it's storing sequences of data, how things progress through time, it can make predictions about what's likely to happen next. A probability distribution of what's likely to happen next. What's the next note in this melody? And it takes that and it passes it down the hierarchy. It basically tells the child, in this melody, you should be hearing this thing next, which, of course, is the name of a sequence for the child underneath it. And what you can do here is you can take a fairly stable, high-level pattern, and it unfolds in time, and then each of those components unfold in time. So I can get up here and just turn a switch on the top of my hierarchy and talk for an hour about brains, creating a very, very complex temporal pattern coming out of my mouth. It's all being driven by my neocortex right now. What you end up, if you train a system like this, you end up with a model of the world. It takes in sensory data and it builds a hierarchical model of the world. We use the word causes. Causes is the term that machine learning people use. Essentially, causes are statistical regularities in the world, things that persist over time that you're exposed to over and over again. You can think of what is the ultimate cause of the pattern on my retina? What's out there? People, buildings, chairs, and things like that. And so you end up with a hierarchical model of causes. That is, there's causes that are small and localized and small in time, and there's causes that are persistent at the top in time over larger areas. We use, and I believe the brain uses a variation of this, Bayesian methods to resolve ambiguity. So you have, essentially, this is a Bayesian network. You can think of it as a belief propagation network. So each node has a little belief about the world. Each node is saying, here's what I think is going on in my little part of the world. And so if I have a sense, and it gets resolved very quickly in a single pass, that's what belief propagation does. So if I have a very noisy input coming in on your ears or your cochlea or your retina or your skin, noisy, things are occluded, and so on. Very rapidly, as you raise up the hierarchy, it becomes very clear that the beliefs at the top are not noisy. They're not ambiguous. And so your perception of the world is very clean and clear. And what surprises people when they actually look at the data coming in on your sensory organs, it's not like that at all. It's a mess. Yet your perception is very clear because you're perceiving what's going on at the top of the hierarchy. What can you do with this? What does the theory tell you can do with this? And I'll tell you how we build this stuff and then what success we're having with it. The theory, just to review what all this does, it says essentially that you build these memory systems, you attach them to some sort of sensory input, and the first thing it does, it has to discover the underlying causes in the data. When you're born, you don't know anything. You can't perceive the world. It's not like you can perceive it and you just can't talk. You just don't perceive it at all. And you have to, through experience, build this model of the world and discover the causes in it. You build a model. This in itself is a very valuable thing. What makes a genius or a really smart person is a person who discovers higher level causes in someone else. You see higher level causes in the world. And you say, aha, I see the bigger pattern here. Someone else. The second thing, once you've built your model, you can do inference. Inference is just pattern recognition. So a new pattern comes in, you say, I know what this is. It turns out most inference in biology is time-based inference. So what I mean by that is you can't understand anything auditorily through your ears unless it moves through time. You can't feel something unless you can move your hands over it. You just will not be able to perceive something. Vision is mostly time-based inference. That is, eyes are moving and people are moving all the time. But it turns out the statistics of vision allow us to do spatial inference as well. So we can take a human, sit them in a chair, tell them to fixate, flash an image in front of their eyes really quickly and say, what was it? And you can do a pretty good job at that. But that's the exception, not the rule. The rule is time-based inference. And in order to do time-based inference, you have their storage of time and sequences and so on. The next thing you can do, as I mentioned earlier, you can do prediction. You can say, okay, given my model of the world, given what's happening right now, what's the most likely thing that can occur? You predict at all levels of the hierarchy. You predict at very high-level concepts like words, so you can predict what word is at the end of this sentence. And then you make low-level predictions like what things will feel like. You're not even conscious of them. A flip side of prediction is behavior. It turns out everywhere in the neocortex, every one of those regions is actually involved in motor behavior. This was something that people didn't really originally understood. They thought it was the motor section of the neocortex. But it turns out all regions of the neocortex are involved in motor behavior. And I'm not going to explain it anymore here, but I can do it in a Q&A if you want. But behavior is the same as prediction. It's essentially it's a generative model that you tie to the machinery below it. So you can actually create motor behavior like robotics and that kind of stuff. It's a very good system for doing attention. You need to do attention at 10 different parts of your input space, and hierarchy gives you a way of doing that. And it's multimodal. That is, works on, of course, the standard biological senses that we think of the three main human senses, vision, auditory, and tactile. But it can work on any kind of system as long as it has the right type of data to it. So this is what the theory said. And the question is, could we build this thing? What do we do about this? So a friend of mine, a guy who was working at my institute, a Stanford graduate student, 3 years ago said, I love this theory. He says, I'm going to try to build this. His name is Dilip George. He's now co-founder of Numenta. And Dilip started with this. Now, if you've seen this before, I apologize. I'm going to show you some new stuff too, but this has been around for a few years. But it's worth showing to you. He said, I'm going to do a very simple vision system. We're going to create a 3-level hierarchy. We're going to have a 32 by 32 pixel space. He's just trying to get this thing to work, right? And the way this hierarchy looked, we had 64 nodes at the bottom of the hierarchy, each looking at a 4 by 4 pixel patch. There were 16 nodes at the second level and then 1 node at the top. He then trained this system on a bunch of line drawings. These are 48 line drawings he made up. And what he would do is he'd take these images, and we'd have to make movies of them. We'd have to show these objects moving around on the retina of this thing, because that's how it has to train. You have to have time to train this system. So he did this. He showed these things moving around. Worked pretty well. And then after we trained the system, we'd give it novel patterns it never seen before. And these are all novel patterns it never seen before. Each column here represents a particular category. And it recognizes all these really well. He says, I know what those are. And you can look at the left-hand column here. You see the dog. You recognize dogs facing left. And we call it a dog. That's not the real dog. Facing left, facing right, a lot of noise. Look at the 6th column over, the one labeled mug. And you go down the last row. You see there's a picture of a mug there that's really noisy. It's almost all just, there's no straight edges or corners or anything. It has no problem seeing what that is. This thing is actually really impressive. I'm going to show it to you right now. I'm going to actually run it for you. It's fun. You can download this off of, let's see here. How am I going to do this? Here we go. You can download us at Numenta's website. And you can play around with it. But I'll just show it to you right now. So this is actually, I'm going to show you, a little front end running a version of this software that's on a server someplace. So we're going over the internet to get to it. And it allows you to draw little pictures. And it's quite fun to do it. So it started out here. Let's see if I can undo the noise on this guy. It started out like this. I'll just recognize this. This is what we call like a stair or something like that. So I'm going to send this pattern up there, and it comes back. And what you get on the right here is a distribution of beliefs. It says at the top of this hierarchy, I think it's the steps. That's my first guess. Then I'll say it's a lamp, and these other things are much lower than that. And then you come in, you can start morphing around and playing with these things. So what I did here a minute ago, I added some noise to this. I said, let's say recognize it again. And it'll come back, and hopefully it'll still say it's probably the steps. But it's certain to be lower. It says, yeah, it's still steps. But I'm not quite certain about it anymore. I can come in here and I can start drawing some weird stuff in here, like this. And we'll pass this up here again and see what it does. Now it may come back and say it's something else. Who knows? I don't know what that would be. We'll see what it thinks it might be. It says, oh, I actually think it might be the little dog here. Let me just clear that and I'll draw a picture. So I'm going to show you me drawing something here. So here I'm going to try drawing this. I'm doing this with a little trackball. So you can try drawing with a trackball. I challenge you. That's a sketch. And put some legs on this guy. This is really bad. Keep my fingers crossed here. Okay. So there we go. It says, yeah, that's a good dog. Now let's try to turn this into a cat. I would say, what's the difference between a dog and a cat? Well, a cat has no legs. So let's just erase one of these legs here. Let's get rid of one of the legs and see what it says. Okay, so now we have a cat. Now, remember, this is never seen these patterns before, right? This is totally new. It says, I still think it's look, cat's coming up. Cat's number 2, but that's still a dog. Well, let's get rid of the other leg and see what it says. We'll leave that there. See what It can be very sensitive. It can be just like you. It can come around and say, hey, look, it still thinks it's a dog. Well, I think the difference is because cats have no necks. You see. And so if I get rid of the head here and just make a headless dog, it probably will think it's a cat. Let's think that. Let's see what happens. It may want me to get rid of that other leg thingy thing that's sort of hanging out there. Yeah, I got a cat. Now it's pretty fun to play around with this thing. And now this is a toy problem, obviously, right? It's not a real problem, but it's a really hard toy problem. This is a hard problem. And I contend there's probably no other way in the world to solve this problem without using hierarchical temporal memories or something really similar to it. Now, I'm going to go back to you can play further with this if you want on your own time. I have to find my presentation again here. Oh, there it is. I'll go back to here. Where was I? I just lost my track here. Yeah, what was I going to talk about next? Oh, I'm talking about that, blah, 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 blah. Yeah, the predictive memory. Is that what I'm supposed to talk about next? I'll tell you what I'm talking about. Oh, here we go. That was the reason it was blank was for me to remind me to go to things. So what do you do about this? So Dilip comes along, and he basically says, look, I can build this stuff. It's kind of crude. It really wasn't a great thing. And I said this theory. I'm a really believer in this theory. So what do we do? So first thing I did was I published a book on this. I published a book called On Intelligence. It came out 3 years ago. It's very easy to read. It's not like a super techie book. It's more biological side. When I wrote the book, I actually didn't know how to build this stuff, so it was more on the biology side. We didn't know how to make it yet at the time. The book's actually had a lot of influence in the world. It's now available in 16 languages, and I get letters from people all around the world who are very excited about it, working on it. I recently found out there's groups in Europe, there's government ones and private ones who are trying to build this stuff, trying to implement this model. I even found there's recently an Iranian website. There's Iranian academics who are building HTMs and so on. You've reached something when you've got the Iranians working on it. Does the UN know about it? But I don't know, but I've been afraid to write to the Iranians because I don't want to send them an email because I think anything that goes to Iran is going to get me in trouble. So I haven't been able to talk to them. They look like nice people. They're just like normal people, academics. They're working on this stuff. The other thing we decided to do is they said, I was running a neuroscience institute for 3 years at this point. And that was a lot of fun. Not, but anyway, it was a lot of fun. And we were making good progress on this, but it was a lot of work. That's what I meant by that comment. But I said, look, how do I get more people working on this? If I'm right about this, I'm willing to place some bets on this. So I said, let's turn it into a technology. Let's try to build a really important technology on it. And we'll use that as a way of getting people excited about it and working on it. So I decided, first I moved the institute to Berkeley because I couldn't run it anymore. So as Terry mentions, it's at Berkeley. We founded Numenta 3 years ago. Oh, I'm splitting the light. More in the light, sorry. Thank you. I was told that was the dark spot.
That's fine.
All right. I thought it was right there, but I missed it. Sorry. So I don't want to block anyone's view here. We formed Numenta in 2005, and the goal of Numenta is to act as a catalyst for this technology and these theories. And you know what a catalyst is, right? A catalyst is a small agent that amplifies a reaction, speeds it up a tremendous amount, and doesn't get consumed in the reaction. So that's the goal for Numenta, to be a small entity that gets a lot of people working on this and doesn't get consumed by it. Because I think it's going to be a very, very large technology. I think it's going to be applied in many, many ways. So we gave ourselves 5 years. We're 3 years into it. A year ago, we created our very first version of this technology. We call it NuPic. I'll tell you a little bit about it here. It was pre-alpha and had many, many limitations. It's hard to use, but we have a number of people working on it. And this year, we're coming out with a new version, which is very sophisticated relative to last year's, and I'll show you some of the development there. And our goal is to build a development community. Our goal is to get thousands of people working on this as rapidly as possible. Okay, so how are we doing on that? Well, first of all, what have we created? One of the things we created, this thing called NuPic, which is the Numenta platform for intelligent computing, right? Now we're in the business world here, okay, right? And NuPic has a bunch of things. One is it's software. None of this isn't hardware yet. So one is we have software that basically manages these hierarchical temporal memories. It's a runtime environment. These are things that are naturally parallel. So we can run this on anything from a single core CPU to a multi-core CPU to multi-core, multi-CPU clusters. The little demo I just ran a moment ago was running on a cluster, but it was actually running on a single CPU on that cluster. So you can do a lot on a laptop, believe it or not. But if you want to do lots of big experiments, you need more processors. So anyway, so the runtime environment takes care of all that. You don't have to worry about it. Then there's a set of development tools that let you configure the network and test the network and so on. There's a third-party company called Vitamin D that's actually created new tools that are better than ours already. So there's an API, and they can plug in their tools and our tools to let you build these things. And finally, the real core to the whole thing is the learning algorithms. And the learning algorithms, how do you store those spatial patterns and how do you store those sequences? It turns out to be very tricky, and there's a lot to be learned in that area. So we allow people to plug them in. We're making a lot of progress on this, but you can experiment with the learning algorithms on your own. And we have a group of people outside of the Numenta who are actually doing learning algorithms as well. And they plug it into the environment. So just a brief thing about this. I'm not trying to sell to anyone. You can download this stuff all for free. Today we have somewhere between 100 and 200 people who use this tool on an almost daily basis. I'm thrilled with that. I would be happy to have 20 or 30 of them right now because it's pretty difficult and sophisticated tools to use. We have 8 corporate partners who pay us a reasonable amount of money to meet with us and get support. Basically, it's a support program. There's applications or people who are trying. I'm not going to say any of them are successful yet, but people are trying all over the map. I've been surprised. We've had several gaming companies come to us. There's one successful application already doing motion capture inference. Basically, how do you have those little ping pong balls on bodies, when you move around? And if you take a snapshot, you just see a bunch of white dots. But if you see it moving through time, you can tell what the person's doing. And this is how they make video games. They record people doing motions and so on. So they wanted to do time-based inference of motion capture data, and it worked very well for that. We have a major car company working on us who's trying to, it turns out a lot of car companies are trying to do this, but one of the major ones is working with us on how do you make a car know what's going on around it, make it aware of what the other cars are doing. And the specific task is, can you predict when a car is going to change lanes in front of you? We have a couple of companies doing, one government contractor doing speaker and voice ID, and we're having good progress with that. Lots of people doing visual type of spatial inference in lots of different types of ways like that. And we have one company doing process control with a company called EDSA, where they're basically trying to monitor power networks, like electrical power grids, and figure out when they're going to fail and make predictions about it, things like that. We've made a lot of progress on this last year. This is a good way to give you a flavor for what this is about. What happened between last year and this year on this? Let's just talk about it. Just give you a sense. I'm not trying to just give you a sense for where this sort of development's going. A year ago, we talked about receptive fields. It's like, okay, a node, what is it looking at? And we had fixed size receptive fields, and they were non-overlapping. It's non-biologically at all. It doesn't look like biology is not like that. So in that the little pictures program I showed you, the different nodes were not looking at any overlapping inputs. They were looking at separate ones. So there's some problems with that. So now our system has gone to overlapping receptive fields of variable size. This is more what biology tells you. In terms of spatial patterns, we made a huge progress here. We used to train the systems almost like a grandmother cell type of training, where there was a single winner. When we did inference, we didn't do that. But when we trained it, we did it that way. And we'd also have to store a lot of spatial patterns. We had to store many, many spatial patterns that the system saw. Well, we've gone to something called two things. One is we've gone to more sparse distributed representations, which are more biologically realistic. And then we're using something called compressed sensing, which is a very clever technology, which is going to be important. Basically, it just shows that when you're storing spatial patterns, so a lot of people work in this field trying to figure out what is a good basis for spatial patterns to represent something. Compressed sensing says you can pick randomly. It doesn't matter. You don't have to have any fancy algorithm. You don't have to figure out what's the best representation or spatial patterns that break up a space. You basically say, pick randomly, and don't pick many. And it works just as well. And lo and behold, it does. It's amazing. So we've now gone to things that are much more efficient, where we use this compressed sensing, and we're much more distributed. And this is both biologically more realistic, and it makes the systems much more scalable. So we can start building very large hierarchical temporal memories. In terms of temporal patterns, storing the sequences of patterns, that's tricky too. And we've tried numerous published techniques for you basically got these noisy patterns coming in. You have to figure out what are the sequences and how to break them up and so on. We've actually been inspired a large part by looking at neurons and neuroscience on this. But where we were a year ago, we had a technique we call a TAM, which is just a temporal adjacency matrix. So you look at spatial patterns and you see how often they follow one another. How often does pattern A follow pattern B? And then you cluster a bunch of those together and you say those must be a sequence because they occur often together in time. But even though we used time in training last year, we actually didn't use it in inference. So everything we did in the past year was only spatial inference. We trained with time, but we had a 0th order Markov chain for actually recognition, so we weren't actually doing temporal inference. Now we're doing temporal inference. We've continued using our original TAM method, but now we're doing higher order Markov chains, and we can now do real time-based inference. And I'll show you a little demo of that right here. Oh, one last thing. We had no attentional mechanisms last year. We now have two. We have a top-down attentional mechanism, meaning when the system begins to recognize something, it feeds backwards down the hierarchy and it pops it out. It says, I'm going to extract that thing, and so you'll see that thing. It's like in your mind, your thing will pop right out at you. It'll do the same. It improves the recognition a lot. And we've also started to implement a fovea and a saccade. And you can get better performance and help do scene segregation using foveas and saccade. I'm not sure that's going to get in this year's release or not, although we've started building it. All right, let me just give you an example of time-based inference. Here's a couple of movies. We're going back to our little pictures demo. In this picture right now, there's actually one of our objects. It's the helicopter. It's in the bottom sort of center or center right of this picture. And there's a lot of noise in this picture, so you may not be able to see it very well. If I just feed this kind of noisy input into our system, you get about a 19% recognition rate, not close to the 100%. That's still pretty good. 19% is pretty good. You might not still see a helicopter. But now, if I show that helicopter moving, so this is going to be a movie. You can see it here. The helicopter is going to move left to right. It just pops out at you, right? Well, you're doing time-based inference. And the same thing happens with us, since we store sequences. And as we do that, and our recognition gets much, much better. It's still not perfect, but it's much, much better. 2.5 times better. We can even go a step further. We'll show you the same movie now, but the noise in the background is going to be dynamic as well. So the objects are going to be moving. Every pixel is going to be changing every time here. Again, you can probably see that helicopter in that movie moving out there. I mean, so can the HTM. And so we over twice as good as we did without the motion there. That just gives you a flavor with time-based inferences. We're using it in auditory and other problems now, but it's basically the core how we do inference in the world. And so any system that doesn't do time-based inference is not going to get very far, even though we can do spatial inference with these systems, as I showed you earlier. We have decided at Numenta to build a prototypical application. We've decided to work on vision, like the cat-dog problem. It's not that we want to be a vision company, but it's a very hard problem. It's very well understood. It's a way of getting people's attention. So we're working on it. A year ago, we were what I've showed you so far: black and white, low resolution, line drawings. It's not very easy to use the system, sort of like the picture of the helicopter there. Today, we're working on grayscale images. We're doing medium resolution, like the image I'm showing here, the car at the bottom. We're using natural objects. We're making a toolkit to make it much easier to customize so people can use this stuff. We're implementing attentional mechanisms, and we're trying to get to the point where people can deploy this very easily, like you can drop this into a website and have it start recognizing things. I'm not at a point to actually demonstrate it live. I hope I was going to do that today, but I can't. But we are going along pretty well on it. These are the kind of categories we train on. These are kind of the images that we're working with. By the way, color is easy. So we're not doing color almost to make it harder for us. Because it's actually easy to add color to this stuff later. Grayscale is not so easy, so that was a big improvement. So here's the kind of categories: cars and boats and shoes and cows and rubber duckies and things like that. It turns out that there are some databases in the world that we can use for training our systems, but they're not very good, so we have to actually work at creating new visual databases because we need to show movies of these objects and so on. And these are just some examples of novel images we clipped off the web that are correctly categorized. So on the left here, cars and boats and binoculars. I don't have any numbers on this yet, at least none that I'm going to talk about. But over the course of this year, we hope to commercialize this. And I don't expect to be anywhere near as good as a human, but I expect it to be a hell of a lot better than anything else. Again, the goal is to sort of be a catalyst for this and get it going and getting other people working on it, getting people excited about it. Not that there isn't a lot of people excited about it, but we need to get to the point where it's deployable and people can more easily work on it. I want to get from about 200 people working on this to 2,000, something like that. We can go back and ask the question: does it solve the difficult problems that Patricia Churchland mentioned earlier in AI? And I think it does. One of the difficult problems was efficiency. Can you store enough information? You have to store a tremendous amount of information. Well, it turns out the hierarchies are very efficient. And the reason they're efficient, both in storage size and in training time, is that the lower levels of the hierarchy are reused over and over again. So when you first train these systems, you're filling in the lower levels of the hierarchy. It's learning the low-level statistical data of the world. And then and that takes a fair amount of time. And after you've done that, it's easy and faster to learn new categories on the top. And the reason is because the low-level features are shared. The low-level causes and knowledge is shared among higher-level features. So once you learn what a bunch of animals look like, a new animal comes along, it's probably going to have fur or skin or scales or eyes and toes and things like that. You don't have to learn all that stuff again. Those statistical lower-level features are already in there. And we've seen this. We have some numerical analysis of this as well, but it's very efficient. It does solve that problem. They're self-learning. Basically you feed in the sensory data, and you've got it all set up properly. They'll extract those causes themselves, and the hierarchies allow them to generalize. So they're able to deal with novel patterns that have never been seen before. My last point on here is one of the most interesting ones, I think, for me, is something I discovered as I went into this. And the question is, why do the HTMs work? What is the underlying cause of this? And the reason is because they make an assumption about the world. They make an assumption that the world itself is structured hierarchically. That the structure of the world in space and time is hierarchical. And you can see this in a body, like a human body. Like I have a torso, arms, and head, and legs. Each of those has substructures. So the head has eyes, ears, nose, and mouth, and each of those has substructure. And their substructure are located near each other in sort of in that tree-shaped sort of form. The world is hierarchical in time as well. You can imagine it easily with things like language or music, where you can see repetitive patterns, words. So for example, phonemes become words, and words become phrases, and phrases become concepts. And those things are used over and over again in a hierarchical fashion. So it turns out the world works that way. This goes back to Turing's thing originally. There's a thing called the no free lunch theorem. The no free lunch theorem says that no learning algorithm, no machine learning algorithm is going to be better than all other machine learning algorithms for all tasks. Meaning you have to customize your machine learning algorithm to the particular task. And I've just described what I think is a sort of almost a universal algorithm that works on all these tasks. But it's not true. It's actually specialized to work with only hierarchically organized causes in the world. Now, if you go back to the computer and that paper tape, as I said earlier, the paper tape made no assumptions about the world. The symbols could be in any order, in any way you want to do it. It made no assumptions. That's what made it universal. It turns out that brains and hierarchical memories are not universal. They are specific to certain types of things, but they do much, much better than Turing machines do for those particular types of problems. And yet they wouldn't work for other types of problems. So you can't use this to solve everything. But it's really convenient that the world, because of the laws of physics, actually has hierarchical structure to it. So almost all the problems you look at in the world that are interesting that in the machine learning area, or at least in the artificial intelligence world, have this, and these things will match to it very well. All right, I'm going to end my talk with just a few thoughts about where this is all going to go, where I imagine it might go. The last chapter of my book was all about this, about trying to predict the future of this. And I don't think we can do a very good job at it. The people who built the very first computers, they couldn't anticipate what we were going to do with them. They knew they were important, but they couldn't anticipate cell phones and GPS and satellites and internet or anything like that. And we're not going to be any better at that here either. But we can talk about where this stuff might go in some other ways. For example, I think we can build really intelligent machines. We're not talking about robots, sentient beings, things like that. Machines that just can solve these problems and understand language and so on. But I think we can deviate from biology. For one thing, for example, we can make our HTMs much faster than brains. Brains are made of neurons. Neurons are pretty slow. They work in the order of milliseconds. But silicon works in the order of microseconds or even faster. So we should be able to do, 1,000, 1,000,000 times faster, make our artificial brains or artificial memories work much, much faster. That'll allow them to solve problems that humans can't solve. We can even slow them down because there's sometimes that humans can't deal with problems because it goes too slow. So we have this ability to tweak the speed. We can experiment with the types of memories we build. We can build the hierarchies bigger and smaller. Nature has done this. All the mammals have a hierarchical neocortex, but they're different. And they have different sizes and shapes and so on. And we can do the same sort of experimentation, but we can do it very rapidly. And we can be able to make them bigger than humans. And we can probably solve problems that humans can't do in that regard. And finally, I think this is the most interesting thing, we don't have to stick with human-like senses. For humans to learn something, we have to turn any other area of interest, we have to turn into visual, auditory, or tactile. That's it. I was in your little virtual reality world over here a minute ago. We have to do that because that's all humans can deal with. But HTMs on their own can deal with all kinds of sensory data. So we can feed in direct weather information. We can feed in financial information. We can feed in manufacturing information. We have people interested in using HTMs to discover what are the underlying causes of yields in semiconductor plants. So you can just feed that data directly into it. And all kinds of interesting things will open up from that regard. So there's a lot of opportunities for playing around with this. And I think we're just at the beginning of this. I think it's going to evolve for many, many years if I'm right about it. I think it's going to be a huge industry. I think it's going to be on the order of the magnitude and impact of computer science in general has been. There's a whole new way of dealing with problems like this. So I'm here for a particular reason. Let me tell you why I'm here. I'm here because I'm hoping to attract 1, 2, or 3 of you, if I'm lucky, to say, hey, that's really cool, man. That's really great. I like that stuff. And then you go to our website and you read the papers and you download the software and you play with it. You might come to our workshop. We're having our first public workshop in June. You can go to that. It's pretty inexpensive. And get involved because I think there's a tremendous amount of work to be done here. I'm excited about it. I want to see this happen in my lifetime. I'm getting older. So I want to keep going at this until it really gets going. So that's why I come to things like this. Hopefully you enjoyed it, and hopefully there's a few of you out there who say, yeah, I want to work on that, because there's lots of opportunities. So that's it. Thank you very much.
Okay, well, thanks for that inspiring speech. This is being webcast, and in order for your question to be webcast, you need to use this microphone. So put your hand up, and I'll give you the microphone.
And if you need to leave, don't. I'm not insulted if you leave. Go ahead.
So, as a Battlestar Galactica fan, I'm worried about you creating Cylons, and so I'm wondering if there are any guarantees of being able to put the first 3 laws of robotics in these things.
Yeah. So I assume you all could hear that question. I don't need to repeat it. I briefly mentioned this in my talk, but there's a long way between creating a neocortex and creating something else. I don't know that term because I don't know the Battlestar Galactica things, but a sentient robot of some sort. Our systems don't reproduce. They have no emotional states other than we have a little switch that says learn, don't learn, learn, don't learn. They have no fear of being enslaved or anything like that. Maybe it's possible for someone to build something like that, and then they'd want to add an HTM to it. But I'm not working on that, and I don't think anyone else is working on that, and that's a long way off in the future if someone did do that. But the real risk, in my mind, is not the kind of stuff I talked to you about. It's things that are self-replicating, and viruses and things like that. But anything that's self-replicating is sort of a dangerous type of thing. We're not doing anything like that at all. There was fears when the steam engine was designed, it was first invented, and there was fears when the computers first came out, and generally those fears didn't come about. And HTMs are like that. They are not dangerous in any way on their own right. It's only when you have someone who's crazy enough to say, I'm going to create some sort of replicating biological structure and put this brain in and make it smart, well, then we might have a problem. But that's a long way away from anything that we're doing right at the moment.
Yeah, you started your talk with the example where it's important to have understanding, like the Mary saw the puppy in the window. It's just not only recognition of the words, but understanding the relationship between them. And in your examples at the end, it's mostly pattern recognition. What are your plans to go toward designing a system which will have true understanding the relationship between the objects?
Well, so the question is laden a little bit because, what is understanding? So you can think of the brain, a human brain, as this large hierarchy. There was 12 levels to the macaque monkey's neocortical hierarchy, right? And the first level is just like in your brain, the back part of your head is basically just doing perception of the world. What am I seeing? What am I expecting to happen next? That's all we're doing at this moment. However, I do not believe that there's anything fundamentally different going on between those low-level perceptual problems and what's going on higher up. The evidence suggests that there isn't. There's some variations going on when you get to the frontal lobes and so on, but not as much as you might think. And the basic theory says that if you can really get a system that can if you build the hierarchy right and you build it big enough and you expose it to enough patterns, that you will actually get to very sophisticated perception at the top and understanding like, what someone's emotional state or what someone's likely to do here and so on. So I guess I'm saying I don't think there's any difference. We're just starting off the bottom. You have to start at the bottom of these hierarchies. And we are just trying to get them to work at all. And the first things you work on are going to be basic things like auditory and visual perception. But I don't think there's no quantum or fundamental shift to go from there to being something that is much more sophisticated than that. It's more just getting the basics right, figuring out how to build it, and then you can make these things larger. One thing that humans do it was in that picture of the macaque monkeys. If you look at you have like an auditory hierarchy and a visual hierarchy and a somatosensory hierarchy. They converge at the top, and they become one big hierarchy. And that was on there. So you actually, if we're just modeling a very simple visual system at the moment. But, we've already got some people trying to do integration of auditory and visual. And then if you do it sophisticated enough, I'm going to argue that real understanding is going to come about. It's not going to be emotional. It's not going to be like a human sitting there saying, I love the view of the sunset type of thing, These systems are emotionless. It's just like the cortex itself is. That's like most of the emotional stuff is handled elsewhere, which the cortex projects to and so on. But I think I don't see any fundamental reasons why we can't make very smart systems that whatever domain we treat them in. Again, not human-like at all. They're not going to have human bodies at all, but they might be really good at math or physics and really smart in understanding what's going on in those things.
So, Patricia?
Yeah, I wanted to explore a little bit further the ideas that you have about attention. And part of what's motivating me here is that it looks like attention, at least the top-down kind of attention, has quite a lot to do with selecting amongst patterns in the environment, so that there might be both a cat and a dog in my visual field, but for reasons having to do with my goals and interests and fears and whatnot, my attention system is going to select one of those patterns rather than the other. Now, in your attention system, it looks like it isn't so much picking out one of amongst other patterns that are there. It looks like it's sort of responding to one hypothesis about what a single pattern is constituted by. So I'm wondering if you can use your system to approximate the sort of selective attention that it looks like in humans and other mammals. Plays a fairly important role.
Yeah, so we are, and I'll try to elaborate on that, although I can't speak with 100% authority on this. First of all, if you had no attentional system and you feed these patterns, and if you feed in a single pattern of some sort, it'll come to the top and you'll get this distribution. It turns out if you feed in complex images with a single fixation, like there's no saccading, there's no fovea, you just put in the whole, like a complex image. Sometimes it'll try to interpret the whole image as something, but if it can't, what it'll naturally do is it'll give you competing hypotheses for the objects that are in there. So it will, even as the system I've shown you now, if you show it a complex scene, if it can't make an interpretation of the entire scene, it will give you the components of it. In fact, even like, I don't know if you noticed, when I drew a little dog, the cat was in there because the cat is a subset of the dog. It's a subset of the dog in there, little pictures. So it actually can do that kind of stuff today. And then what happens is you get a choice at the top. You say, look, I think I see 5 or 6 different things out there that I recognize. Then at the top you can say, well, I want to pick one of them, and then that one will pop out and become clear. Just some other things that might be useful to think about here. I just skipped my mind. I was just about to tell you something.
Feedback connection?
Well, I'll talk. It'll come back to me in a second. The other type of attention, the overt attention, which is where your eyes are moving in the fovea, actually play a big part in this as well. Because when you look at a complex scene, you have to, your eyes move around, and because of the fovea overrepresents certain parts of the field, those things are going to be more likely to be seen, and so on. So, our belief is you got to have both of them. You got to have the top-down, which can select among multiple hypotheses, and you have to have the bottoms-up sort of saliency detector looking around the scene. And we don't think we can have a commercial-grade vision system if you don't have those. So we are in the process of implementing them right now. I thought I had another interesting comment to say, but I can't think of it right now. But it's a good point, Patricia, and we got to solve it, and it seems to be working pretty well.
Okay, question here in the corner.
Okay. Now, in the biological brain, because of the obvious limited capacity constrained by the skull, we might have more reasons to forget. But in the HTM, it's not constrained by any physical limit. Does the system forget?
Yes. Does the system forget? This is a very interesting point, actually. It turns out the system's always forgetting because you don't want to remember everything, right? And as you go up the hierarchy, you're actually shedding knowledge about the low-level aspects of the world. You're saying, I think this is a nose, and I'm going to forget the details of it, and so on. So you're constantly forgetting stuff. In fact, the whole purpose of generalization is to generalize means to not pay attention to the details as being different, but to recognize as being something similar to what I've seen before. So we can build bigger memories. I'm not sure we want to have them remember more. I'll tell you something we can do, and which is very interesting. You can tweak the learning algorithms, and by tweaking the learning algorithms, you can have it generalize more or generalize less. And if you have it generalize less, it remembers more data. It's called a hierarchical support vector machine. You basically degenerate to a hierarchical support vector machine, and it becomes a very efficient way of storing lots and lots of specific data, but it doesn't generalize it all. And I believe this is what happens to people who have savants. They can remember tremendous amounts of detail. They have a brain that looks just like yours. It's just something different about it, right? They can literally memorize thousands of books. This is documented stuff. Thousands of books, every word on every page. Yet they don't generalize well. They don't see the innuendo. They don't, so on. So this theory explains how that can happen. You can tweak these one way or the other, but I don't think you can have your cake and eat it too. I don't know how you can save everything and yet still generalize. You have to sort of choose a bit. Now, I'll add one more thing to this. There's a whole bunch of other parts of this theory that relate to other parts of the brain. One is the hippocampus, which is very much involved in memory formation. And we have a very simplistic view of how the hippocampus, what it's doing to neocortex. If I look at an HTM, and at any point in time, it's got some pattern coming in, and it's recognizing what's going on, and it may not be remembering anything, it's doing inference. If you could take a snapshot of the states of the different nodes in the hierarchy, like what the current beliefs in each of those nodes are, it's a very, very efficient way of storing, in some sense, that image of the world. It's like saying, okay, I've got this thing coming in, I'm at the top, I have this high-level concept, I'm seeing a dog. But if I could snap out, take the individual states of all the nodes in the hierarchy at that point in time, and put them in a buffer over here, and then later I could reinstate them, I would visualize that dog exactly like it was. And I would remember the details. And we think something like this happened with the hippocampus. We've modeled this. We've tested it. It's a very efficient way of saying, okay, all this data is coming in. I'm not remembering most of it. I'm not remembering most of it. I'm not remembering most of it. I want to remember this right now. You just take it off to a buffer off to the side. And then you can later just reinstate it. And all of a sudden, the whole thing comes right back. It's like, So it's a related question. So if I wanted to make a system that stored a lot, I would still have the hierarchical memory the same way, but I'd build a bigger sort of hippocampus equivalent. I'd take more buffers off to the side and be more specific. All right, I'm going to take one more question.
One question back here.
Okay, maybe I'll take 2 more questions. I'll do that one and this one.
Okay. Yeah, thanks for the talk. I found it's really interesting. I'm going to download the software and try it out. So still got one person. So just want to make a comments. I feel there is a little bit detachment from the title of the talk because the title of the talk is Computing Beyond Turing. but end of the day, we're still running algorithms on top of Turing machines. So
yes, you caught me.
So I wanna pick up your brain on questions like if we really want to go beyond Turing, do you think the model, how we make computing hardwares or architectures is going to be the first thing we want to solve, or is there a possibility that by using individual computing system, traditional computing system like we're using today, just on the higher level to make them more interactive, exchange information in a more sophisticated way, we're going to grow into a non-Turing machine. So which way is going to be?
I'm not sure I understand the question, but let me try to answer and see if I address it. First of all, you made the observation that I said beyond Turing, but then we're running this on traditional computers, right? True. We're using the universal Turing machine, can model anything else, to model hierarchical memories, and so Turing predicted that, and he was right. I never saw Turing was wrong about that. So that's obviously the way to get started, But one question is, do we want to do it that way for all time? That's one question. And there's quite a few people interested in taking this theory and these models and turning them into hardware. And I'm interested in that too. For example, modeling HTMs on a Turing machine is not necessarily very efficient. The hardware and the way traditional computers work is not really designed for this. Turns out the memory that we store in HTMs are all large, sparse matrices. That's what the memory looks like. You can think of it as neuron connectivity matrices. It's very similar to that. But the large, sparse matrices, and almost all the computation is multiplying a matrix times a vector and getting the result. So, one thing that struck us very early on said, gee, well, maybe we should design memories, the physical memory itself, to be like that. You could design physical memory, whether it's chips or hard drives, whatever, to be more aligned with the sparse matrices and have the operation, the most common operation, done in the memory itself. So instead of reading the matrix out and then multiplying it, just pass the vector in and get my result type of thing. So there's a whole bunch of clever things I think will happen over time to actually start building these things using non-traditional computers, because it'll be more efficient to do so. And we haven't done so today because, even though there's a fair amount of interest in it, is because it's too early. We're still trying to figure out how it works, right? We're still playing around. It's a lot easier to play around in software than it is in hardware. But I think that will change, and actually there's a couple of initiatives I know of already who are trying to do this in various ways in hardware. Now, I think your question was a little bit more involved than that. It had to do with, would we want to merge this kind of HTM with traditional computing type of stuff? And I say absolutely, if that's what you're asking. I have no idea what's going to happen. But, all kinds of weird stuff could happen. You could do a distributed HTM over the internet where everybody's computer is a node and doing various things. And I haven't a clue what that means. But we could definitely, add these capabilities to traditional computing products. We'll certainly do that. A car that can recognize when other cars are about to do something dangerous is going to be connected with a regular computer and so on. So did I get close to answering your question? Good. Actually, I'm going to end it there. I'll take your question offline. I want to thank you for your time. I appreciate you to come here.
Okay, well, let's thank Jeff again. And if Jeff is right, if the HTMs are in your future, then someday an HTM may be your best friend.
There we go.
Thanks, Jeff.
All right. Do I have time?